Hello YouTube, welcome to this installment of the Evian blog. So today on the Evian blog, one of the first pieces of equipment that I've managed to reacquire was a Hitachi V212 20 meg analog scope that we'll be using for some of the audio and low frequency experiments alongside the PC based scope for the moment until I acquire a new DSO. And something else that has been quite nice is a friend of mine gave me a Matrix MFG8216A function generator. Now it has a few issues, one of the issues being that its maximum output is about 1 volt peak to peak. So there's definitely something wrong because it should output more. The waveforms seem to be okay. I know I had a problem with one of these exact devices in the past where the top half of the waveform was fine and the second bottom half was distorted. And I discovered it's because of the dual rail power supply. It's got 2 voltage regulators in the back, so I replaced the one, made it work again. This one we're getting a clean waveform, no matter which one you choose, right through to the point of 2 transistors. Now, to cut a long story short, I have removed these two, well, one's an NP and one's a PNP transistor, for testing, etc., and found them both to be bad. And I have some in stock, so we're going to fix it up and we're going to see how this thing runs, and if it runs properly, happy days. A basic 1-2 megahertz function generator on the bench for experimenting, etc. So let's jump straight into it. And I'm sorry it's not very detailed in the repair procedures and how we traced it, because unfortunately I cannot find schematic diagrams for this thing, so I'm just going by intuition, knowing that I'm seeing a signal reaching these transistors but I'm not seeing the signal getting away from them, so intuition tells me there's a problem there. And when I check the transistors with a normal multimeter, I'm finding the collector emitter on both the NPN and PNP are not registering as a junction, so there's definitely something wrong there. But let's get back to the bench and have a look-see. Hey everybody, so this is just something I've been working on for a little while. Forget about the little fan at the back here, etc. I'm going to replace all of that. This signal generator, this is a matrix function generator, the MFG8216A. I believe it does up to 1 megahertz, just over 1 megahertz. It'll do sine square, it'll do TTL CMOS logic, duty cycle, etc. So it's a very basic signal generator, and I've been working on this for a while because it does have a few issues whereby the output was always running very low. You'll see we've done some mods over here to connect a fan in, which is working alright, but not ideal, obviously. We will solve that. But where things get interesting over here is we've replaced these voltage regulators over here, but they still get very hot, which is part and parcel of the design, I think. Now, the main issue that I was having is the output was running sort of less than 1 volt peak to peak on full amplitude. Now, let me just go on to the measure on the scope. We are talking about, we're on 5 volts per division, and I'm getting nearly 20 volts peak to peak. Now, on a multimeter, let's just see what the multimeter shows as an AC sine wave. Putting out the scope now. Actually, no. Let me screen capture the scope of how it's performing now. So this is the output fully jacked. Let's just go to measure mode. Frequency, we should be getting around 1 kilohertz. Period, no, we don't need a whole bunch of stuff. We want frequency, we want peak to peak, and let's get an RMS as well. And then I'm going to do a screen grab so you guys can see what we have here. 1.005 kilohertz. clean. Yeah, output is definitely there. And it's turned down at the moment. We can go to full, but everything seems to be stable. So the beauty is these two transistors, NPN and PNP, yeah, it's an NPN, that's a PNP, are the amplification stage for this little knobby over here. So what we're going to do now is we're going to switch to a live view on the scope. Now before, like I said, I was getting less than a volt peak to peak with this thing turned all the way up. So let's go live to the scope, and I'll get a camera on the front display of this and overlay it, and we can see exactly how it's performing now after we changed out these two. And for those of you that want to know how I diagnosed that there's something wrong with these, simple procedure, multimeter, both of them were open circuit between collector and emitter. Both of them registered base, but collector to emitter we had open circuit, no 0.6 drops or anything like that either way. So bad, replaced them, removed all the dodgy glue, put the heat sinks back on, and let's show you how it's performing now. Hello YouTube. So back to the signal generator. You'll see over here these sort of bodged on transistors with their heat sinks. I had these small signal transistors in here. I replaced the ones with the original ones as per what the specification and what came out. I've blown 2 full sets of these in a day, so I'm not sure why. I've checked power supply, everything looks good. Maybe I just got a bad set of these PNP transistors because they seem to be the cause every time. And subsequently, tip 41C, tip 41D, I'm not sure if we're going to get our 1 megahertz out of them, but for what I'm using it for, this is sufficient. They had to be wired somewhat cross-legged inside, yeah, because obviously the pin layouts of a TO220 package is different from these little fuckers over here. So some additional adaptation had to be made to get all of this firstly into focus. There we go. And then of course into there. They weren't getting as hot as these small signal ones were, but just as a matter of recourse, I thought it probably a rather good idea to pop these heat sinks on here, and we just see how it performs. These guys are definitely not getting anywhere near as warm as the other ones. Beautiful thing now is on low we are reading around 1 volt RMS or 458 millivolts peak to peak. Switch the scope to high, well, to times 10, and then we'll run it at 5 volts per division. See what we get out of it now. Right, more than what was expected. Let's put it this way, it's more than the original setup was, but in so saying, I'm not sure if we're driving them too hard or whatever. We're now getting 21.176 volts peak to peak out of these little guys over here, and an RMS of 16.3 volts RMS. Now that seems a bit excessive for what I'm doing, so I'm turning it down to a lower peak to peak value. In fact, let's bring it right down to around a peak to peak value of about 5 volts peak to peak. Okay, in fact, no, let's drop this and drop that to 10 times to 1 times probe, and let's see where we can go with this. Let's run it at about a peak to peak of about 3 volts. That's more or less 3 volts peak to peak at 1 kilohertz. So now what I'm going to do is I'm going to start running up on the frequency things. and we're going to see how this goes. I do need some screen recorder software. In fact, let's see about going handheld over here. Right. Here we have the scope waveform. Please excuse the handheld footage. So we're going to go 10 kilohertz. Right, there we got our 10 kilohertz. And it's registering as 10 kilohertz, no problems at all. Come on. You can do it, Captain. The only thing I dislike about PC scopes is when you've got a slow bloody PC. It can be awfully painful. Catch wake up, Captain. Let's stop it and restart it, and I think we've got a lockup. So let's close her up. Open her up again. And let's go to 100 microseconds. Right now we've got our 10 kilohertz, no problems at all. Let's go back to measure, frequency, and peak to peak. Peak to peak should be 3 volts still. Yeah, 3 volts, 10 kilohertz. Right, so now we're going to run it to 100 kilohertz. Well, it's 107.97. I'm not too sure about the stability. Let's switch this up a little bit more. Okay, 110 kilohertz registering there. More or less, but the waveform is still showing our 3 volts peak to peak. So let's take this down to 5. Right, there it is. Stability is lacking a little bit over here. 1 megahertz. Let's see what happens. Okay, we got our 1 megahertz. Yep, it is reading as 1000 kilohertz on the base. 1 microsecond. There it is. Triangle. Sawtooth. What? Oh, that's triangle. Square wave. Square wave really doesn't look like a square wave at 1 megahertz, but what can be expected from this thing? And there you have it, ladies and gentlemen. So, when we go back down to our 1 kilohertz, boom. We firstly need to drop this right back down. And let's make you run at 500 microseconds, and there you have it. So we got 500 microseconds per division. So we should use up 2 divisions for a full cycle, and there you got it. From here, 1 division, 2 division, 1 kilohertz. Spot on. Fantastic. It's quite interesting how things work now. Now I've done some work on this thing, so I may have been to blame for some of it in the past, but needless to say, I'm not sure. But we're going to get this thing back together again. Humpty Dumpty. Right, so we've got a stable signal coming out from our signal generator. Now I can put everything back together. Well, not everything, I'm just going to put the base plate on so that the board doesn't get any damage, because it looks like tomorrow we're going to be quite busy and in and out, so I might not get straight back onto the fan portion of this repair, upgrade, whatever you want to call it. Okay, one more here on the front. Bob's your uncle. Okay, getting that back together. Powering up. And we have our signal. Set it to sine wave. And there it is. Bob's your uncle. Very, very nice. Now it's just the cooling solution we need to sort out. And hopefully these will not run too hot. Everything seems fine. And then of course this one on the back here I'm hoping runs a little bit cooler now. Yeah. Now we also have a 24 volt point down here on the board, which if I'm not mistaken was originally designed for the fan. So we're going to check the voltage there. 24 volts. Wow, that was interesting. We've lost signal and we've burnt out our transistors again. Why would that be? I can actually smell the transistor this time. Let's just check it. But it's actually starting to piss on my battery. Ooh, I'd be pleasantly surprised if we survive that. Ha! Looks like the transistors did survive, they did. So what is the issue we're having back here? All I did was I probed down here on the board and it caused everything to go fucking bananas. So it's a 24 volt power rail. Very concerning actually. So it appears that there is a mechanical issue here somewhere. And it smelled like something burnt out there. Maybe I saved its ass, who knows. Again, this is a 10 mega ohm resistive load. We should not see any issues whatsoever. And it seems to be okay now. Weird. Right, so we're sitting with 25.7 volts on this rail. It's not regulated, but regulating a rail is not a problem. Everything seems stable. Now to run that fan we need a clean 5 volt signal. We can either regulate off somewhere there or we can do something else. Let's just see what voltage we're sitting with on the transistors at the moment and try and do this without burning everything up. We got 15 volts here and this power supply is not happy here. minus 15 volts there. She's definitely not a happy chappy. Although these transistors are surviving it this time round. So hopefully nothing too severe. We shall get that resolved. Now I'm a bit concerned as to why we had power rail goes funny now. Anyway, let's just crank this up. And balked. It's getting fucking irritating actually, because now the issue is rearing its ugly head again. The interesting bullshit. Yes, I literally touched this. Here we go again. Now, some magic smoke has escaped from this area here. So we have an idea. There may be some damaged passive components over here. Just going to wait for these transistors to cool it, and then I'm going to see about letting some magic smoke get out so that I can see. The thing is, I'm noticing down inside here there's two little resistors, and this one looks like it's just gotten rather hot. So I'm not too sure what those resistors are for. Maybe we need to look at putting some new ones in there. Let's pull the circuit apart and see what those are actually for before we do that. Right, back in we go. Noddy. See if we can get a take on them from up here. Very difficult positioning. We're showing a 6 ohm there. Now the question is, should it be 6 ohms? Well, fuck knows. You can't get a damn schematic for any of this cheap Chinese shit on the internet, so it's near impossible to tell if that is correct or not. And we get 6.94 ohms on the second one, but they're getting hot. What the fuck are they doing? Let's see, the two are connected together and they go to the bottom of the board. Well, don't they fucking always? A circuit diagram for some of these things would probably be pretty damn brilliant when it comes to fault finding, repairing these things, but sadly many of the manufacturers don't give us those luxuries because they expect us to purchase a new one. Well, fuck you, Matrix, wherever the hell you are. I'm not going to be purchasing a new one. This one's either going to go in the bin, get repaired, or modified, or whatever I need to do to make it happen. I must admit, I'm a little bit irritated that the design can be so poor in something such as this, but what else can you do, eh? Alright, so let's follow those resistors. Here we get the trannies. What the fuck is going on here? Here's the one, here's the other. So the output from these two transistors, oh wait, fuck it, let's get a bit closer to the board here.
try. Can we see that? Get this shit out of the way. There we got it there. Okay, how far in can we go before the picture gets blurry? Oh, that's not bad. Okay, so here you have the bottoms of these two transistors kicking over here. And these resistors are here to here, then they bridge together, and then here. And here we go, our power supply coming in. This is our power supply into these transistors. You've got a positive and negative voltage rail. You got your base signal coming in here from another split marginal motherfucker over here. Goes in base, driving the two to create a positive and negative path of the cycle. The output comes here, goes through these resistors, merges up in the center on the top of the board. Where it goes from there, nobody knows. An interesting calamity is there doesn't appear to be any sort of forward point from there onwards, which makes this a rather interesting nightmare to deal with. Here's a closer view over there, you can see them there. That little guy over there and that little guy down there. They're actually looking a little bit toasty at the moment, so that's where the magic smoke is kept. Now, the output across those two resistors is technically the output from these trannies over here. So maybe it's too much power, I don't know, but they did look a bit cooked before I changed to these, so I'm thinking maybe we need to change those out for something. Play with a few values and see what we can do with the output to get it to work. It's always worth a try. So in no uncertain terms, those resistors are going to be removed from circuit. Purely because I want to figure this flipping thing out before it drives me totally insane. Although the solder in here does seem to melt quite low, I am finding it always a little bit easier just to add a little bit of solder before you come in with a solder sucker and pull that bastard's teeth. This little fucker's teeth seem to be in there quite good, to be honest. So after some delicate dental surgery with a flat screwdriver and a pair of needle nose pliers, we got the two little bastards out. We got the two open and the four holes are pretty clear here. So, the idea being we put a pair of resistors in there and we see what happens. Now, I don't know what value is meant to be in there. You can't make those out anymore for the life of them. So, next step, something of interest, the output to ground. And we've disconnected the grounds obviously, so we should have fuck all resistance to ground. And at this point over here we're showing 8K to ground. This should be the same, 7.9. Why the fuck is the difference? 7.945, 7.945. Okay, so both of these where the two come together shows 8K to ground. So we've got an 8K load already, so some low value resistors in there I think will do good. Something with a little bit more backbone. Good morning YouTube, and welcome back. We're back onto the signal generator. I am just getting ready to do some testing. I've just basically replaced the two resistors. corner. This transistor I'm not happy with. This one's still pretty sturdy, but that one I'm not. You'll see down inside there, I've just replaced this little boy here, that little boy over there. We'll see now what happens. I don't understand why this guy keeps flopping about in the breeze, but that's the way the cookie crumbles. So. Okay, so we are generating 1 kilohertz. We have the output tapped up. The out is going into a 50 ohm pair, well, more or less 50 ohm pair of resistors. And we are sitting with 11.1 volts peak to peak on the output. Transistors, still cool. Resistors, still cool. Regulators, warming up a little bit, but you can touch them now. I do feel maybe once the fan is installed things will improve there. We're not getting any drop off, which is fantastic. I am quickly going to set up Open Broadcaster, and then I'll be back and show you guys the actual scoped output from this thing in real time while we're doing this test. I'll be back now. Right, so here we have, you can see as I tweak the knob, you can see the values decreasing right down. So we're starting at around 240 millivolts peak to peak at the bottom. Okay, then we can start sliding up, and as you can see it rapidly increases. So I'm just going to switch the scope probe to ×10. Okay, trigger's a bit low, but it'll pick up now, and there we go, all the way through to just over 10 volts, well 11 volts peak to peak. And it's been running like that now for probably around a half an hour. No issues, no problems at all. The 2 transistors are still cool. The regulators are hot. And the resistors are running cool. So I'm hoping we've resolved the issue. Don't know what I'm going to do to secure this thing from flapping in the breeze though. I'll have to do something there. We'll work it out. So guys, I think there we go, we've got our fix sorted out. So now the next thing I need to do is modify the top chassis for the larger fan, and possibly also just give it a few once overs with a soldering iron to clean up any dry joints that I encounter, or whatever the case may be, because there's some funny issues going on here. But yeah, everything's looking handy dandy. Very nice. Thanks for watching. 1.005 kilohertz. Clean. The output is definitely there. And it's turned down at the moment. We can go to full, but everything seems to be stable. Okie dokie, boys and girls. So on the screen over here, which I'm going to pull up and I'm going to duck down to the corner, you'll see we're sending out a 1 kilohertz signal from the signal generator. Let's just see here. Stop the measuring. Oh yeah, okay, let me show you what we got here. At the moment we've got 1 volt RMS verified on the Fluke 189. Going out, there you'll see on the voltmeter on the top we've got 1.00 somewhat change RMS. Everything's looking pretty accurate over there. If you look down here on the right, near the bottom of the screen, you'll see total harmonic distortion 0.093 somewhat percent total harmonic distortion at 1 kilohertz. So that's pretty good. I'm quite happy with that. We can check out a few other bits and bobs while we're here.
Let's just have a look, see here. Frequency, we've got exactly 1 kilohertz. We've got a resolution of 10 hertz. We can give ourselves a resolution of 5 hertz. But 10 hertz kind of gives you a nice quick result. So let's go to a counter. There you've got your hertz counting up. At the frequency counter, we're running at 1 kilohertz, 1000 hertz exactly. So yeah, as you can see, everything's looking pretty good over here. We've got 1 kilohertz, we've got pretty much everything. Total harmonic distortion is low. Nice noise view, very low. If you look here on the spectrum analyzer, you'll see not a whole lot of, let's just get all this other crap out of the way. You'll see not a whole lot of harmonics. We've got 1 kilohertz, something at 2, a little bit more at 3, a little bit more at 5, but at 1 kilohertz we've got a nice signal. I am going to increase this a little bit more and just see if the distortion picks up. We'll get around 1.5 RMS, and as you can see there on the bottom on the spectrum analyzer, we've got quite a few transients coming up, but below 1 volt RMS things look pretty good. In fact, if you go below sort of 0.25 volts or 0.2 volts RMS, you'll see it's actually quite a clean signal. So yeah, not too shabby. Quite happy with that from this matrix function generator that I've been fixing. I'm going to do a few more tests on it, but as you can see by what I'm showing you, things are looking pretty good and I'm very happy so far. Thanks for watching, everyone.